Good morning to one and all. Good morning. So please kindly confirm audio video on screen once. Please kindly confirm audio video on screen once. Clear? Fine, fine. So let's continue with that fourth chapter what I have said in the previous class. That is a transient analysis on the transmission line. Transient analysis on transmission line. Okay. See, particularly transient analysis on the transmission line means and which type of model we have to consider. And what model we have to consider this means only distributed model. Okay, right. Transient analysis on the transmission line means we have to take this as a distributed model of transmission line. Distributed model of transmission line, we can say. Okay, yeah. See, listen. So I will be showing up that approximate distributed model to you. Approximate distributed model. Distributed model, right? So in the previous classes also we have seen this RLCG circuit parameter model like this. RLCG circuit parameter model. So like this we have number of sections connected in cascade. Okay, number of sections connected in cascade, something like this, right? And so on in this manner. Right, next thing. So let me tell you. So this is the point at which we will be keeping the voltage source. Is a point at which we will be keeping the voltage source. Right. So it's a source, I can say. And this side, you might be having a load, whatever it is. Receiving end side, we might be having a load. Okay. So these are per kilometer line constants, RLCG, we are taking up. RLCG per kilometer line constants. Per kilometer line constants, we can see. Okay, next thing. Listen. So I will ask one very simple question here. Very simple question. At time t equals to 0 plus, we are closing the switch. Time t equals to 0 plus, we are closing the switch. After closing the switch at time t equals to 0 plus, which wave is going to be released onto the transmission line? Which wave is going to be released onto the transmission line? Is it the voltage wave to be released onto the line, or current wave to be released onto the line, or both voltage and current waves? Yeah, which wave is going to be released onto the line? So I'll say both voltage and current. Not only voltage, both voltage and current waves are going to be released onto the transmission line, and those are going to be propagated towards the receiving end side of the line. After looking at the receiving end side, there may be a possibility for change in the voltage and the currents. Okay, yeah. So I will say first, after closing the switch, at time t equals to 0 plus, I'll write both voltage and current waves. Voltage and current waves will be released onto the transmission line. Will be released onto the transmission line. Will be released onto the transmission line. Okay, so after closing the switch at time t equals to 0 plus, both voltage and current waves will be released onto the transmission line. Done. Next thing. Look here. Irrespective of load, whatever the load you have, is the open circuit, having some load, short circuit, doesn't matter. Irrespective of the load, just after closing the switch, you know both voltage and currents are going to be released onto the transmission line. Okay, next thing. Simple. I'm standing at this place. standing at this place. I am asking one simple and silly question here. Just listen. By staying at this point, at time t equals 0, switch was closed. How much distance the waves might have traveled? How much distance the waves might have traveled? 0. The waves have not traveled any distance by staying at this point only. So I can say x equals to 0. For example, these waves are crossing one section. These waves are crossing one section. How much distance the waves might have traveled? 1 kilometer length. 1 kilometer length. And if the waves have traveled two sections, I can say it will be 2 kilometers length. And towards the end of the line, we can say x equals to L. X equals to L. Please kindly understand. Please kindly understand. The same model we have drawn in case of the what we call steady state analysis also in the ABCD calculation. In the ABCD calculation, particularly in steady state analysis, we have drawn the same model, but we have shown x equals to 0 at the receiving end side, x equals to L at the sending end side. X equals to 0 at the receiving end side, x equal to L at the sending end side. But here we are starting our analysis from sending end side. We are starting our analysis from the sending end side. So I am showing x equals 0 at the sending end side, and towards the receiving end side, it will be x equals to L. X equals to L, you can see. Okay? Yeah. Listen now. See, in case of network analysis, you might have studied two types of transient analysis. One is DC, other one is of AC. Here also, we have one is AC, other one is of DC transient study. But what is the difference? What is the difference between transient analysis done in the network analysis and transient analysis what we are doing now? Anybody please tell me. What is the difference between transient analysis done in network theory and transient analysis in the present? Yeah, please tell me. Model is different. What is the model on which we are doing transient analysis in case of network theory? Lumped model, but now we are doing it on the distributed model, right? So that's the simple clarity what we need to have. Okay, we are doing transient analysis on the distributed parameter model. Moreover, I will be concentrating only on the DC transient study. DC transient study. The results of the DC transient study can be extended for AC also. So for our understanding, first what I will do is, I will consider only lossless line by removing this R and G. We will consider only lossless line, only LC elements cascade connection. I will take. Onto that line, we will be putting one DC voltage source. And by putting the DC voltage source, we will see how that voltage and currents are getting created and are getting propagated towards the end of the line. Okay. So after that, we will take some load and what will happen to voltage and currents. All these things we are going to discuss further in this transient study. Okay. Yeah. So first I am going to take up the heading like DC transient analysis. DC transient analysis is the first heading I am going to take up here. DC transient analysis. Yeah. So I am saying again, this is particularly on a lossless line. On the lossless line, we are going to discuss about this. Okay, let me draw that lossless line for you. So this is approximate model. So we have an inductor, capacitor of the first kilometer or first section, you can say, or first meter also you can assume, that's your wish. Like that we have number of sections connected in cascade. Number of sections connected in cascade, something like this. Okay, so I'll call it is L1 C1, L2 C2, Ln Cn, And this is a point at which we will be keeping that DC voltage source, right? So it's a plus minus voltage V. And this is a point we have already mentioned x equals 0. And this is a receiving end side. I will be keeping this as x equals to L. And this is a switch to be closed at the time t equals to 0 plus. That is a switch to be closed at time t equals to 0 plus. Okay? Yeah. So rather than going with this approximate, if you want to draw this as exact model, I will be showing that line simply in this manner. Simply like this, I am showing the model. Right? So like this we have. So I am showing DC voltage source here. It's a point x equals 0 and this is the receiving end side x equals to L. Like this you can say. It is a more exact model what you have to understand. That's what I'm saying. But the upper model is for our understanding. This model is for our understanding and this is the exact model what we can see practically speaking. Practically speaking. Okay. Yeah. So let's continue. Let's continue. See, before starting this transient study, yeah, listen. So before doing this transient analysis or transient study, first we should write the initial conditions. What are the initial conditions of the system? Initial conditions are very simple to write here. We don't have any stored energy in the transmission line wire. There is no energy stored in the transmission line. That's the initial condition what we are going to keep now. Okay, right. So I can say initial condition will be no energy stored in the transmission line. No energy stored in the line. No energy stored in the transmission line. No energy stored in the transmission line means what? Anybody please tell me. What do you mean by no energy stored in the transmission line? So that is nothing but half Li square value 0 and as well as half CV square value is also 0. Half Li square is 0, half CV square value will be also 0. That's the meaning. Okay. First one is, see, half Li square is equal 0 means which value will become 0 now? Is it inductance or current? Half Li square value was 0 means which value will become 0 now? Is it inductance or current? Inductance value will not become 0 anyhow. Current should become 0. Current value should become 0. And similarly, half CV square is 0 means which value will become 0? Is it capacitance or voltage? Capacitance will not become 0. Voltage will come to be 0. Voltage will come to be 0. Means initially there is no existence for the voltage and currents on the transmission line. That's the meaning. Initially there is no existence for the voltage and currents on the transmission line. So all of a fresh, we are injecting the voltage or we are injecting the source onto the transmission line at the time t equals to 0 plus. This is understanding what you have to get. Okay, now tell me please. After closing the switch at time t equals 0 plus, after closing the switch at time t equals to 0 plus, what is the behavior of this inductor and what is the behavior of the capacitor? After closing the switch at time t equals to 0 plus, what is the behavior of inductor and what is the behavior of capacitor? Anybody please tell me. Inductor is going to act as open circuit. Why? Why in the sense we don't have any current existence, right? Initially at time t equals 0 minus, we don't have any current flow. So inductor will not accept sudden changes in the current. So the current in the inductor will be as it is of time t equals to 0 minus condition. So current equals to 0 in the line means this inductor I will say acting as open circuit. And what about capacitor acting as short circuit? Why? In the sense, initial voltage value was 0. Okay, so I can write here. So at time t equals to 0 minus, or at time t equals to 0 plus, just after closing the switch, inductor acts as open circuit, and capacitor acts as short circuit. Capacitor acts as short circuit. Inductor acting as a open circuit, and the capacitor is going to act as short circuit. Okay, next thing. Please kindly listen. Very simple to understand. Don't complicate it. Very, very simple to understand. Okay, one more thing I want to tell you in this one. One more thing. All these inductances will be equal. All these inductances will be equal, and you write it is L Henry by meter or kilometer, whatever it is. Capacitance values also equal all. Okay, you can write this one C. It's in farad by meter. C in farad by meter. Okay, please tell me now. At time t equals 0 plus, the switch is getting closed now. L1 acting as open circuit, C1 will be acting as short circuit. Next, look once, please. Then what is this voltage at time t equals 0 plus? All of you please tell me. What will be the voltage at this place? 0, right? Because capacitor is acting as short circuit, or there is no voltage on the line. But what is this voltage? Just now we have closed the switch. Just after closing the switch, this voltage will be V. And you observe now, a voltage V minus 0. Voltage V minus 0 appearing across the inductor L1. Because of this voltage gap, current starts flow in the inductor. Current starts flow in the inductor is nothing but current starts flow in the transmission line. So according to the equation, like inductor current equals to 1 by L integral of VL dt. VL is a voltage across the inductor, right? Integration of that with respect to time multiplied with 1 by L will give the inductor current. So the inductor starts carrying the current, and I can say the inductor is getting energized. To some value, something like half L1 I1 square we are writing. Half L1 I1 square. Okay, so I can write in the next slide. L1 starts gaining the energy, or you can say L1, inductor L1 will be energized to half L1 I1 square. Inductor L1 will be energized to half L1 I1 square. Yeah, in all models it is same. In all models, L is open circuit, C is short circuit. That's it. In all models, L is open circuit and C is short circuit. Okay, listen please. See, whatever the current I1 we have now, that current I1 should pass through capacitor only, C1. Why it is so means we have a short circuit here and we have an open circuit here. We have a short circuit and we have a open circuit, so that this current I1 will be flowing through this capacitor C1, or it is closing its path. It's closing its path through the capacitor C1. Okay, so whenever it is closing its path in that manner, definitely capacitor starts energized. So that there is some voltage development across the capacitor, something like V1. Voltage development across the capacitor, something like V1. Okay, so this the people will say like the energy stored in the inductor will be discharged to capacitor. Energy stored in the inductor will be discharged to capacitor, or half L1 I1 square converted into half C1 V1 square, so that this voltage starts rising up. Okay, so I can write here. So as I1 current closes its path through C1 comma. So C1 will be energized. C1 will be energized to half C1 V1 square. Of C1 V1 square. So that implies you can say half L1 I1 square will be converted into half C1 V1 square. Okay, half L1 I1 square will be converted into half C1 V1 square. Practically through air, it will be completing the path. Charging current is a path for the current circulation. Charging current is a path. Okay, next thing. See, this voltage starts rising up. This voltage starts rising up here. What is this voltage? 0. This voltage will be obviously 0. And we have a potential gap again across the inductor. So as we have the potential gap across the inductor, definitely we have a current of I2 in this now. And the current I2 is circulating through capacitor C2 definitely. So there is a development of voltage V2 here. So that this voltage starts rising up to a value like V2. Right. Again, in the next section, we have a current of I3 and then a voltage of V3 and so on up to the end. We have a IN and we have a current voltage of VN. Like this, the voltage and currents are continuously changing on the transmission line wire once after closing the switch. All of you getting this one? All of you getting this one? Please tell me. Right? So initially L1 is open circuit. But there is a voltage across it. Because of that voltage, current starts developing in the inductor. That current is circulating through capacitor. Because of the current flow in the capacitor, voltage starts developing across the capacitor. If that voltage is developing, that voltage will appear across the next inductor. So the second inductor will start carrying the current. That current will flow through second capacitor. So second capacitor voltage starts increasing. And that second capacitor voltage will appear across the third inductor. So third inductor starts carrying the current. That current will flow through third capacitor, developing the voltage. Like that, we can observe continuously voltage and currents are developing on the transmission line. By the exchange, kindly observe here, by the exchange of inductor energy to capacitor energy to inductor energy continuously. There is an exchange of electric energy to magnetic energy and then magnetic energy to electric energy continuously on the transmission line during this transfer. Okay, so if you want, you can write as a statement half L1 I1 square. Just now you said it is getting converted to half C1 V1 square and it's getting converted to half L2 I2 square and then converted to half C2 V2 square and so on. So this is that energy conversion happening. That's the energy conversion happening. Okay, so you can write now. So are you observing any voltage and currents movements on the line? Are you observing any voltage and current movement on the transmission line? Yes or no? So simply current I1 in the first section jump to second section as I2 with some time gap. What is the time gap? Means energy store and discharge time gap. And that I2 jump to third section as I3 and so on up to the end. IN. There is a movement in the current. Similarly, voltage first section V1 jump to second section V2, next V3 and so on up to Pn. There is a movement of the voltage on the transmission line. So I can say here. So after closing the switch at time t equals to 0 place, after closing the switch at time t equals to 0 place, I can write both V comma I waves will be released onto the line. and propagated towards the end. Propagated towards the end. Towards the end. Okay. You please tell me now. Please tell me how much time? How much time? Yeah, tell me please. How much time this voltage and current waves are going to take to reach the end? How much time this voltage and current waves are taking to reach this point? Means x equals to L. How much time it will take? Generally, what is the definition for time from physics? From physics, what is the definition for time? So it is nothing but length by velocity. Length by velocity. Length means what? Length of transmission line. Length means length of transmission line by velocity, in the sense velocity by which the wave is going to be propagated. Velocity by which the wave is going to be propagated. Right. So I can write here. I can write here. Time taken by the wave. Time taken by the wave. By the wave to reach. Wave in the sense anything, it is a current wave or voltage wave. Simply you can write electromagnetic wave, EM wave, electromagnetic wave, to reach end of transmission line. So capital T is equals to, it is length of line, or you can say distance traveled by the wave, length of transmission line, or you can say distance traveled by the wave by velocity of the wave propagation. Velocity of wave propagation. So I can write from this, it's a length of line L by velocity of the wave is V. So that velocity of the wave already we studied, no, it will be 1 by root LC meters by second. 1 by root LC meters by second. Yeah, so I think all of you are understanding this. Okay, next thing. So let's continue like this. See, strictly speaking, just after closing the switch at time t equals to 0 plus, you are saying that voltage and current waves are moving, right? So this movement of voltage and current waves, strictly the people use it to say electric and magnetic energy flow. Electric and magnetic energy flow by continuous conversion from one form to other form. By one form to other form. This is what we'll say sometimes as electromagnetic wave propagation also. This we can say as electromagnetic wave propagation. Okay, anyway, I am not going to write that term, but you have to remember it. Simply, it's like an electromagnetic wave propagation. Next thing, kindly observe. See, second section I am talking. Second section, half L2I2 square is the energy. Half L2I2 square is the energy. Capacitor, half C1V1 square. Half C1V1 square is the energy. Can I say half L2I2 square is equals to half C1V1 square? Because we don't have any loss in the discharge, right? There is no loss in the discharge path. There's no loss in the discharge path. So I can say half L2I2 square value, half C1V1 square value. These two will be equal. Next thing, half C1V1 square, half L1I1 square. These two will also be equal because we don't have any loss in the discharge path again. Following all of it. So in that perspective, half L2I2 square equals to half C1V1 square, half C1V1 square equals to half L1I1 square. Finally, what we can write is half L1I1 square, half L2I2 square, half L3I3 square, half Ln square. All these energies are equal. All these energies are equal. Okay, so I can write now. So by the observation, we can call half L1I1 square is equals to half L2I2 square, and so on up to the last section. We can say half Ln IN square, half L and IN square. And already we said all the inductance values are equal. You can cancel it and you can get here currents I1, I2 and so on up to IN. These are equal. Let us say it is current in any one of the section. Let's say it is current in any one of the section. I1 equals to I2 and so on up to IN. Let's say it is I current in any one of the section. Current in any one of the section. Similarly, you observe here, half C1 V1 square, half C2 V2 square, and so on up to half Cn Vn square. All these are equal. All these are equal. Yeah, let me check. Once. Similarly, half C1 V1 square equal to half C2 V2 square equals to, and so on up to half Cn Vn square. Half Cn Vn square. So from this, you can call it is V1 equal to V2 and so on up to Vn, which is V, which is nothing but V. V1 equal to V2 and so on up to Vn, that is nothing but V. That's nothing but V. Okay. So I think all of you getting this thing? All of you getting this? Next. So I will discuss a very, very simple topic here. Simple topic further. Kindly understand what I am saying you now. Yeah. So I'm moving to lossless line may not be practical. That's okay. Lossless line may not be practical, and you have a variation in voltage and currents. That's it. Throughout the length of the line, you don't find the same magnitude of voltage, same magnitude of current. There may be a change. That depends upon the attenuation. Okay. Yeah. Or if I am showing, Shraddha, please complete it. See, listen. So I'll take one lossless line model, right? Just look here. Just look. It's a very, very simple one to understand. It is a lossless line model we have. And this is a place at which we are about to keep the voltage source V, DC voltage source V. And look here, please. At time t equals to 0 plus, we are closing the switch. Time t equals to 0 plus, we are closing the switch. Okay. See, after closing the switch at time t equals 0 plus, at section 1, let's say, section number 1, maybe x equals to 1 kilometer, I am standing, x equal to 1 kilometer. Voltage is coming as V1 symbol, current is coming as I1 symbol. After closing the switch at time t equals 0 plus, current flow started, voltage development also started in the line. And at that point of 1 kilometer, I am experiencing that voltage V1, current is I1. What is the relationship between these two? What is the relationship between this voltage V1 and current I1? Anybody please tell me. What is the relationship between voltage V1? Yeah, this is a practical thing only. Practically, the energy exchange will happen in this manner. Yeah, I am asking you this question. Please tell me. What is the relationship between this V1 and I1? That will be decided by the energy exchange only. That will be decided by the energy exchange. Yes or no? Because, in the first section, as an approximation, we said that half L1 I1 square converted to half C1 V1 square. And who is the cause for this voltage V1? The current I1 is a cause. Voltage V1 was caused by current I1. Second section we say current I2 caused by whom? Voltage V1. Following all of you. So I can say here, half L1 I1 square value is equal to half C1 V1 square. So this is a way of getting that conversion. That's a way of getting that conversion. Yeah. See, from this, you can see here V1 square by I1 square value is nothing but L1 by C1. So you can have V1 by I1 here is a square root L1 by C1. V1 by I1 is equals to square root of L1 by C1. L1 by C1. Okay. But already you said, voltage and currents are same throughout the length of the line. That we are saying simply VI. Voltage and currents are same throughout the length of the line. That is nothing but V and I. So let's say at some point on the transmission line or at any point on line, kindly observe me, at any point on transmission line after closing switch, voltage is V, current is I. Now you please tell me, in general, what is that voltage to current ratio? What is that voltage to current ratio? That is nothing but square root of L by C. Right? Voltage to current ratio is nothing but root of L by C. So what we call that V by I generally, what we name that P by I generally, impedance. That impedance we are calculating or we are finding during the surge operation. We are doing that in the surge operation. Hence, we are going to call this root of L by C as surge impedance. Or you can say sometimes as it's a natural impedance of the transmission line. So this root of L by C, as we said earlier, it is known as surge impedance of line, or you can call this as natural impedance of transmission line. Natural impedance of transmission line. Okay. Surge impedance, or you can say natural impedance of transmission. Next thing. Just try to understand what I am saying. Try to understand again. Same diagram I will repeat. This one, lossless line model. Very simple discussion. Please don't complicate it. Please don't complicate this one. Just listen what I am saying you. Thinking in different ways will make a complication here. Just observe. Surge impedance of this line is, let us say, 200 ohms. Stop writing, please. Just listen. Surge impedance of this transmission line wire is 200 ohms. This voltage, 200 volts. Listen please. After closing the switch at time t equals to 0 plus. After closing the switch, listen all of you. After closing the switch at time t equals to 0 plus, a voltage V gets propagated on the line. Similarly, a current I gets propagated on the line. Yes or no? Voltage V gets propagated, current I gets propagated. How much voltage gets propagated along the transmission line? Or how much voltage will get developed along the transmission line? How much voltage gets developed along the transmission line? Tell me please. That will be 200 only, na? That will be 200 volts only. So we have a development of 200 volts along the transmission line at all the places. So we have a development of, I can say, 200 volts. How much current gets created? How much current gets created now? Please tell me, how much current will be created? That is given by this conclusion what we have made. V by I equals to root of L by C, so-called ZC. So how much is ZC number? 200. So if you take voltage to current ratio, that will be ZC. So I can say current I is equals to V by ZC. So you get this value as 1 ampere. You get that value as 1 amperes. Right. See, if you talk in the what we call propagating way, just listen. First we injected 200 volts. How much current is getting created? Means V by ZC. So 200 by 200, 1 ampere. 1 ampere current is getting created. Then because of that 1 ampere, how much voltage is getting created? Because of that 1 ampere, how much voltage is getting created? I into ZC. I is 1 ampere. ZC 200. So 200 volts is created. Because of the 200 volts, how much current is getting created? 200 by 200, 1 ampere. Because of that 1 ampere, how much voltage is getting created? 1 into 200, 200 volts. Like that, voltage and currents developing along the transmission line are same throughout the length till we reach to the end of the transmission line. The 200 volts, 1 ampere, 200 volts, 1 ampere will be continuously developing on the transmission line towards the end. Towards the end. Yeah, have you understood this phenomena? Please kindly tell me. Have you understood this phenomena? It's not a flat line. It's not a flat line. Flat line comment you should make only under steady state. Flat line comment you should make only under steady state. In this transient condition, you should not make a comment of flat line. Okay. Next thing. Next thing. Listen here. Listen. I think most of you might be knowing, and we have discussed also, surge impedance is independent on length of line. Why? Surge impedance is independent on the length of the line. Why? Why that surge impedance is independent on length of line? Anybody? Yeah. Nobody is responding. Why that surge impedance is becoming independent on the length of the line? It is the root of L by C, and you say sometimes I multiply inductance with length and capacitance with length, and length will be cancelled out. Length and length will be cancelled out, so that we can say ZC is independent on length of line. Is it? But you see, surge impedance. Please listen all of you. Surge impedance value, is it defined at only one place on transmission line or throughout the length? Surge impedance, is it getting defined at one place on the line or throughout the length? Tell me, please. It will be defined at one point only, right? Not throughout the length. Why you are saying throughout the length? We are standing at this point, and you should check what's the L value here and what's the C value here. Root of L by C at this point is a surge impedance, right? Yeah. Have we multiplied with length here? No. Kindly observe all of you. We are standing at one point and we are taking L, C at that point for that conductor configuration. And we are taking root of L by C. That is a surge impedance at that particular point. It's not going to be defined throughout the length of the line. Throughout the length of the line. Yeah, all of you getting this? Please tell me. Yeah, next thing. Kindly observe. See, if L and C values, if inductance and capacitance values are same throughout the length of the transmission line, if the values of inductance and capacitance are same throughout the length of the transmission line, then we can say this surge impedance will be also constant throughout the length of the line. And surge impedance is independent on the length of the line. And it will be same at all places on the transmission line during the propagation. All of you getting my words? Right? If L and C values are same throughout the length of the line. Throughout the length of the line means maybe per meter. L per meter, L per meter, L per meter, L per meter, L per meter. C per meter, C per meter, C per meter, C per meter. If L per meter, C per meters are same throughout the length of the line, then you can say that surge impedance will also be same throughout the length of the line. Then who will decide whether this L and C are same throughout the length of the line or not? Who will decide whether this L and C values are same throughout the length of the line or not? That is decided by size of the conductors and spacing between the conductors. Size of the conductors and spacing between the conductors. Right. So if the size of the conductors and spacing between the conductors is same throughout the length of the line, the surge impedance of transmission line will be constant throughout the length of the transmission line wire. So I think all of you getting this? Okay. So I can say here, ZC is independent on length of line. ZC is independent on length of line or constant throughout the length. constant throughout the length if radius of conductors and spacing between conductors is same throughout the length. Same throughout the length. The radius of the conductors and spacing between the conductors is same throughout the length of the line. Then I can say this ZC is becoming independent on the length of the line. What's the name of ZC here? What's the name of ZC? Yeah, please tell me what's the name of ZC? Characteristic impedance is one term we said. Characteristic impedance. Okay. Please listen now. See, I will say this ZC as characteristic impedance of the medium. Characteristic impedance of the medium through which the wave is propagating. Characteristic impedance of the medium through which the wave is propagating. Who will decide this characteristic of the medium? Who will decide the characteristic of the medium? Material and dimensions. Material and dimensions. Yes or no? Material means material by which the conductor was manufactured, surrounding dielectric medium, and size of the conductors, spacing between the conductors. These are the terms which is deciding the characteristic of the medium through which this electromagnetic wave is going to propagate. Following all of you? Right? So ZC is the characteristic of the medium through which wave propagates or it's a characteristic of medium which causes for a continuous conversion of electric energy to magnetic energy to electric energy, vice versa. Okay, so it's a property of the medium. Also you can write characteristic and property, both are same names. Property of medium which causes for continuous conversion of electric energy to magnetic energy, vice versa. So this point we should be very clear about the characteristic impedance, which causes for the conversion of voltage to current and current to voltage, voltage to current ratio that we are defining as ZC. This point we should be very clear, very clear. Voltage to current, vice versa. Okay. So next, for example, look here. So this is a transmission line which we are discussing now. This line, we are going to terminate with some load. See, till now what we have done is we have closed the switch at time t equals to 0 plus, and we said that a voltage V and a corresponding current I, so called V by ZC, propagated towards the end of the line. I don't get any change in the voltage and currents during the first propagation. Why? I don't get any change in the voltage and currents of the first propagation. 200 volts will be developed along the line at all places. 1 ampere current is getting developed along all places on the line towards the receiving end side, so-called up to the time t equals to capital T. Why? What's the reason? What's the reason? Please tell me. After closing the switch, again lossless something, some unnecessary statements you are saying. Already we said lossless long back. Huh? Why you are saying unnecessary statements? Again, no load. What is the point of no load? I didn't discuss anything about load. Kindly understand what I'm saying you. After closing the switch at time t equals 0 plus, voltage V 200, current I 1 ampere. Without any change, these voltage and currents are developed throughout the length of the line up to the receiving end side. Why? ZC is same throughout the length of the line. That's the reason. Why you are not getting any change in the voltage and currents? Means there is no change in the values of, there is no change in the value of characteristic of the medium. Characteristic impedance remains same throughout the length of the line. That's the reason to say that voltage and currents developing are same throughout the length of the line in the first propagation. Have you understood this? I need your response. If you didn't understand this one, it is very difficult to understand the further extension of this. All of you understood this? Characteristic impedance, surge impedance, you can use any name, no issue with that. Surge impedance is a type of characteristic impedance. Surge impedance is a type of characteristic. Yeah, okay. So now let us take a type like this lossless line, what we are discussing now, is terminated with a resistor or terminated with some load, terminated with some load. Yeah, so let's take next heading, lossless transmission line terminated with resistor, I will say, with load resistor. Lossless transmission line terminated with a load resistor. Yeah, simple, very simple thing. This is that lossless line what we are talking now. Lossless line having same surge impedance throughout the length of the line. By assuming that radius of the conductors is same throughout the length, as well as spacing between the conductors is also same throughout the length. And this is a voltage source. We are showing V, DC voltage source. And this is a point of x equals 0. And this is a point of x equals to L. And switch is getting closed at time t equals to 0 plus. And as it's a lossless line, surge impedance is in which nature? Which nature? Resistive in nature. Surge impedance will be in resistive nature. And at the end of the line, means at x equals to L location, x equal to L location, I am keeping a resistor ZL. So I am keeping a resistor of ZL. Like this we can say. Yeah. So please listen now. Please listen. Same explanation, whatever we have done earlier. Okay. Please look here. Please look here. What is the definition of ZC? Definition of ZC. It's a property of medium which causes for conversion of voltage to current, current to voltage. That's it. What is ZL definition? In the similar way, what's the definition of ZL? What's the definition of ZL? This will be again same. It's a property of the load, property of the load or property of this medium, which causes for the conversion of voltage to current, current to voltage. Voltage to current, current to voltage. Yeah, yeah. Maybe you can say characteristic impedance of the load. Characteristic impedance of the load. Listen, listen. Time t equals 0 plus switch was closed. Voltage V will be propagated. How much is the current to be propagated? V by ZC, that's it. V by ZC. After reaching to the end of the line only, it will face ZL. After that voltage and current waves reaches to the end, then only those voltage and current will face the ZL. Else it will be experiencing ZC only. It will be experiencing only ZC. Okay. So a voltage V will be developed on the line. Correspondingly, a current of I, V by ZC will be developed on the line. So that voltage V, current I will be propagated towards the end of the line. Towards the end of the line. Okay, and this is a point what you will say as junction of line and load. Junction of line and load, or you can say discontinuity point sometimes. Discontinuity point. Because after reaching to this point, the voltage and currents, whatever it is getting attacked here, experiencing a load. Experiencing a load. Experiencing a load. And this ZL value, whatever you have shown here, might not be equals to ZC. This ZL value, what we have shown here, might not be equals to ZC. At the time, what will happen? At the time, what will happen? Definitely, there is a change in the electric and magnetic fields. Definitely, there is a change in the electric and the magnetic fields. Because of that change, there will be a change in the voltage and the currents. Definitely, after the waves have been reached to the junction. Reach to the junction. Right? So I can say the voltage and currents, resultant voltage and currents after reaching to the junction might be modified to V2 comma I2. Might be modified to V2 comma I2. Might be modified to V2 comma I2. For the condition of what we are talking now, ZL not equals to ZC first. ZL not equals to ZC. So we will be writing that statement. All of you understood this point? I will explain it again. I will explain it again. ZL not equals to ZC. ZL not equals to ZC. Yeah. Look here. Look here. Very simple thing. ZL not equals ZC. Voltage and currents V comma I reach to the junction facing a discontinuity. Facing a discontinuity or facing a change in the characteristic impedance of the medium. Right. So after the V comma I waves, reaches to the junction. After the V comma I waves reaches to the junction, a discontinuity faced by these waves, right? And causes for change in voltage and currents. Change in resultant voltage and currents. Resultant voltage and currents. Causes for change in the resultant voltage and currents. Okay, let's assume that the resultant voltage and currents are V2 comma I2. In bracket you write V2 comma I2. Resultant voltage and currents are V2 comma I2. See, one very simple logic here. This is one point where we are standing. Look please. This is one point where we are standing. Just before the point, we have some voltage. Whatever it is. Just above the point, we have some voltage that I am saying as something like V2. Just above the point, I am saying the voltage as V2. New voltage, what we have been experiencing. What should happen to the voltage before to this point? What should happen to the voltage before to that point? Please kindly tell me. Just above the point, voltage is V2. Just before the point, how much should be the voltage? Must be V2 according to KVL. Not V, it's V2, V2. Just follow the notation. Follow the notation. Saying V. Right? It will be V2 according to KVL application. According to the KVL application. See, in the similar way, V comma I waves propagating towards the end of the line. Voltage wave we talk. Voltage wave propagating towards the end of the line, reaching to the junction. After reaching to the junction, ZL and ZC are unequal. There is a change in the property of medium. Change in the property of medium. Because of the change, resultant voltage is becoming V2. Resultant voltage is becoming V2. Then you please tell me what should happen to voltage on the transmission line? What should happen to voltage on the transmission line? Will it be at V or V2? Will it be V or V2? Definitely modified to V2. Definitely modified to V2. Following all of you? Right. Definitely this voltage will be modified to V2 because of this resultant voltage what we are getting. Right. So I can say, in the vicinity of the junction, right? Just after the voltage wave was attacked, resultant voltage is V2. So the voltage on the transmission line from that point onwards should be modified to V2. The voltage on the transmission line should be modified to V2. See, as usual, it will change. It will change. Practically speaking, it will change. But for our mathematical study, I will be assuming that a voltage V1 is added to V. Voltage V1 is added to V in such a way that this V plus V1 is equals to V2. But practically speaking, there is no meaning of this adding V1. There is no meaning of adding V1. After reaching to the junction, resultant voltage is V2, then voltage on the transmission line might be modified to V2 continuously. So I think all of you getting this. Is it okay? So I'm writing that point here. Yeah. To satisfy KVL in the vicinity of junction, a voltage V1 is added to V mathematically. Voltage V1 is added to V mathematically such that V plus V1 is equal to V2. Such that V plus V1 is equal to V2. V plus V1 is equals to V2. Similarly, please tell me. After reaching to the junction, what is the outgoing current you are saying? I2. Outgoing current is I2. But what is the current just before the junction? You are saying it is I2. KCL was not satisfied. So in fact, what you should think is, after reaching to the junction, current was changed to I2, then current on the transmission line before the junction, current on the transmission line must be modified to I2. Automatically, it should be modified to I2. Automatically, it will modify, but mathematically, on the paper, we are going to add a current of I1 to I. We are adding a current of I1 to I, such that this I plus I1 is equal to I. I plus I1 is equal to I. So I'll write the same statement. To satisfy KCL in the vicinity of junction means in and around junction. That's the meaning. Junction. a current I1 is added to I in bracket mathematically, okay, such that this I plus I1 must be matched with I2. I plus I1 must be matched with I2. V2, so means from this point, what you should understand is a time t equals 0 plus V comma I propagated on the line. After reaching the end, the resultant voltage and currents are what? V2 I2. Then from the time capital T onwards, voltage and currents along the line will be modified to V2 I2. Reaches to the one more junction here, right? Because we have a source here. Source will not accept to have a change in the voltage. Because this voltage is fixed at V. This voltage is fixed at V. Then from that point onwards, what will happen? Voltage will be modified to V, current will change. Again, reach to the end. Again, we have a discontinuity. Change in the voltage and currents. Comes back. Right. Again, we have a change. Like that, at some point, it will compromise and it will settle down. Where you say we reach to steady state. Where we will say we reach to steady state. And particularly, this V comma I, what we have here, are going to be called as incident. V comma I are going to be called as incident. V2 I2 called as refraction, or you can say transmission. Refraction, or you can say transmission. V1 I1 we call it as reflection. V1 I1 we are going to call as reflection. In the general notations, V comma I will be named as incident. V1 I1 reflection. V2 I2 are going to be called as refraction, or you can say transmission. Refraction, or you can say transmission. So from this, in this explanation, what we have made, you should write refraction V2. Refraction V2 equals to incident plus reflection. Incident plus reflection. Similar way for the current also. Refracted quantity is equal to incident quantity plus reflected quantity. Reflected quantity. So refraction V2 I2, incident VI, reflection V1 I1. Reflection will be V1 I1. Like this, you can say. Okay. I need a perfect explanation from you. What will happen if ZL equals to ZC? I need a very perfect statement from you. If ZL and ZC values are equal, what we should say? If ZL equals to ZC, what we should say? See, listen, please. Listen, please. If ZL and ZC values are equal, after the waves have been reached to the end of the line, after that voltage and currents reaches to the end of the line, these waves are not facing any change in the propagation medium. These waves are not going to face any change in the propagation medium. As it don't have any change in the propagation medium, there is no change in the voltage and currents to be experienced. So I can say V2 I2 will be exactly equals to V comma I. Is it required to add any numbers mathematically to make up this? Is it required to add any numbers mathematically? No. So there is no existence for V1 comma I1 values in that situation. That the people will say no reflection. The wave will not experience any reflection if load impedance and surge impedance are exactly equal. If load impedance and surge impedance are exactly equal. Okay, yeah. So let me write here. For ZL equals to ZC, for the condition of ZL equals to ZC, the wave will not face any waves will not face any change in propagation medium at junction J. Waves will not face any propagation medium at the junction J. So V2 is equal to V, I2 is equal to I. That implies V1 0, no reflections will be experienced. No reflections will be experienced. Yeah. Yeah, I2 equals to I. It's not 0. I'm really sorry. I2 equals to I. Refracted quantities and incident quantities are equal. Refracted and incident quantities are equal. No reflection. Okay, next, for example, now the case what we have to concentrate is obviously ZL is not equals to ZC. We have to concentrate here, ZL not equals to ZC. Okay. See, do you get all these things in steady state analysis? Checking whether the wave is reached to the end of the line, what is the reflection, refraction, all these things, is it required to study in steady state analysis? No. See, if we have some load at the receiving end side in the steady state analysis, in one shot, I will go with ABCD. In one shot, I will be going with ABCD and I will be doing analysis with ABCD. That's sufficient. You don't need to discuss about how that wave is propagating or not. Yes or no? Right. Fine. Let's continue. See, I have to find out the values of V2 comma I2, for any value of ZL given, irrespective of ZC, for any value of ZL value given at the receiving end side, we should have a capability of getting V2 comma I2, Okay, yeah. Please listen. To find out this V2 comma I2, I will be thinking in the application of Thevenin's theorem. Thevenin's theorem is nothing but with respect to this junction J, I want to find the Thevenin voltage as well as Thevenin impedance. Thevenin voltage means open circuit voltage I have to calculate. Okay, so open circuit voltage I should calculate with respect to the junction. How to find out Thevenin impedance? You find out Norton current. Find out the Norton current, or you can say short circuit current. Right. After getting the short circuit current, the ratio between the VOC and ISC will give you Thevenin impedance. With the help of these things, we convert or we construct a lumped model. With respect to junction J, which is valid only for the time t equals to capital T. By using that circuit, we'll find out V2, I2, and then we find out V1, I1 values also. I don't know whether you have understood this or not. Very simple thing. To find out the values of refracted quantities V2, I2 for any value of ZL given, we are about to construct the Thevenin equivalent circuit. We are about to construct the Thevenin equivalent circuit. Okay. So for the Thevenin equivalent circuit, we want to find open circuit voltage and then short circuit current. Please go through the previous classes notes, Balavignesh, once I discussed about ZC. Yeah, please listen. Please listen. Time T, just now we discussed, no, that's a propagation delay. This one, propagation delay. Propagation delay. Yeah. So let's continue. Let's continue. So now, first I will be taking up open circuit line wave propagation. Next I will take up short circuit line wave propagation. Then, based on results of the two, we construct the Thevenin equivalent model. Yeah. First heading I am taking up open circuit line wave propagation. Open circuit line wave propagation. Yes. Open circuit line wave propagation. So I will show the approximate model of the line, so called L and C elements. L and C elements like this. This is the first section. Right? So like that we have number of sections here. Yes. Yeah. So this side we are keeping one DC voltage source. V point of x equals 0. The switch to be closed at time t equals to 0 plus, you can say. Each and every section is having same values of L and C. Each and every section has equal values of L and C. It is x equals to L, receiving end side. And open circuit in the sense, you know, ZL is equals to infinite. Open circuit in the sense it will be ZL equals to infinite. ZL equals to infinite. Yeah. Okay. Okay. Very simple. Very simple. Yeah. Else, if you want, I will show that exact equivalent. Sorry, exact distributed model also. Can say like this. Exact equivalent model. The light plus minus V. There is a place at which the switch is going to be closed, and this is a receiving end side where you know ZL value was infinite. Like that also you can. Listen. ZC. So what is the nature of ZC for lossless line? What is the nature of ZC for lossless line? It will be resistive, right? It will be resistive in nature for the lossless line. Lossless line. Okay. Next. After closing the switch at time t equals to 0 plus, you know, there is no initial energy stored in the line. So the current starts developing as well as voltage also starts developing. I'll say a current of I starts flowing with a voltage V. So we have a current I and a voltage V here. It's a current I and it's a voltage V. And this is a junction J. Junction J. That's a junction J, for which I can say we have an incident of V comma I. For which we have an incident of V comma I. Okay. And how much time it has taken to reach this point? capital. How much time it has taken to reach that point? Capital T, which is nothing but length by velocity of the wave propagation. Next thing. So I can write at time t equals to capital T, or sometimes you say capital T plus also. See, in the power system analysis, particularly in the transient study, what we are discussing, there is no difference between the capital T time and capital T plus T. There is no difference between the time capital T and capital T plus. Both are same. At time t equals to capital T, or after reaching to discontinuity, or after reaching to junction J. After reaching to the junction J, you can say. Yeah, kindly observe now. Kindly observe. See, incident voltage and currents are V comma I, definitely. There is no doubt about it. Incident voltage and currents are V comma I. V comma I. But what we are facing at this junction J, open circuit. We are facing open circuit at the junction J. Okay. See, open circuit we are facing as ZL is equals to infinite, or you can say open circuit. What you know generally in the open circuit, is it voltage or current? See, refracted quantities will be V2I2. I will show that symbol, then I will ask about the question what I said. V2I2, reflection will be V1I2. I am asking the same question now. After reaching to the end, we are facing the open circuit. What you know in the open circuit? Is it voltage or current? Open circuit, what you know? Is it voltage or current? I think I know current. I don't know about voltage. I don't know voltage in the open circuit, that I have to calculate, actually speaking. But current I can say easily, that is 0. Open circuit current equals to 0. So I can say definitely this current I2 will be equals to 0. Definitely that current I2 will be equals to 0. So current I2, refracted current will be equals to 0. Refracted current equals to 0. So after saying that the refracted current is 0, incident current is I, we can find out the reflection current. You can find out reflection current. What is that reflection? You can write. That is nothing but refraction minus incident. Refraction minus incident. Okay, reflection is I1. Refraction 0. Incident I. So we have a reflected current of negative I. We have a reflected current of negative I, minus I. Reflected current of minus I, minus I. Done? Reflected current of minus I. Okay, next. See, listen all of you. Listen all of you. Just look at this circuit. Look at this circuit. After the switch was closed at time t equals to 0 plus, a voltage V is getting developed along the line. Voltage V is getting developed along the line, and we have a current of I. We have a current of I as well as we have a voltage of V, like this. And we have reached to this point, so called the junction. We have reached to this junction J. Okay. And we have a refracted current I2 0. Refracted current I2 equals 0. See, outgoing current is 0. Outgoing current is 0. Then what should happen to incoming current? If the outgoing current is 0, what should happen to incoming current? Incoming current should also fall down to 0, right? Yeah, understanding or not? Yeah, is outgoing current equals 0, so obviously incoming current should fall down to 0. But there exists a current of I, you are saying now. There exists a current of I, you are saying that current I what we have, that should fall down to 0 now. That will fall down to 0. Following all of you. First of all, you tell me why there exists some current initially in the transmission line. At point capital T we are talking. the point of capital T we are talking now, right? Why we are having this current in the transmission line? Because of the magnetic energy storage. Because of the magnetic energy storage, there will be some current existing in the line. Because of the magnetic energy storage, there will be some current existence in the line. But after reaching to the receiving end, means X equals to L, we have an open circuit, outgoing current equals 0. So current in the transmission line must be zero means the magnetic energy stored in the line. Magnetic energy stored in the line might be converted into electric energy. Magnetic energy stored in the line might be converted into electric energy, right? Because of that conversion, there is some extra voltage developed in the transmission line. There is some extra voltage developed in the transmission line. So the resultant voltage on the transmission line will start rising up. Okay. Yeah. So I'll say here. So as ZL equals to infinite or open circuit at receiving end side, open circuit at X equals to L, right? The outgoing current I2 equals to 0, you write simply. Refractor current equals to 0, right? So the current in the transmission line, must become 0. Must be 0 from capital T time onwards. Capital T onwards. But physically what will happen? Is, so the magnetic energy stored in the line, must be converted into electric energy. Magnetic energy stored in the line must be converted into electric energy, right? So that conversion, what I am saying here is half CV square is a new electric energy developed on the behalf of this half Li square. Half Li square was converted into half CV square. Half Li square was converted into half CV square. And you can write now V square here is equal to 1 by 2 was cancelled out. L by C into current square. V square is equals to L by C into current square. And what that new voltage developed here? I into root of L by C, na? And that root of L by C is nothing but ZC. Okay, V is equals to I into ZC. What do you mean by that I into ZC? That is nothing but capital V. So this voltage is capital V. So this is the new voltage development. New voltage developed on the transmission line. What are the already existing voltage? Capital V, right? Already existing voltage is capital V, and this new voltage small v, adding together makes that voltage as small v plus capital V. That will be 2 times of capital V comes. 2 times of capital V. So you can say the voltage will be doubled. So therefore, resultant voltage on transmission line will be small v plus capital V, which is capital V plus capital V. So this number will come to be 2V. That number will come to be 2V. The current will exist up to the capital T time. Up to capital T time, current will exist in the line. From capital T onwards, current starts becoming 0 continuously on the line. Voltage will be rising up to 2V. Yeah. So can you please tell me? Can I call That voltage itself is a resultant open circuit voltage. Whatever the 2V you got now, can I call this itself as a resultant open circuit voltage, so-called refracted voltage? Somebody saying yes? Yeah. So this itself we can say as refracted voltage. Refracted voltage, or we can call open circuit voltage. At what time? At what time we are talking now? Capital T time. Capital T. Is it our aim of calculation here? Is it our aim of calculation? Anybody? Is it our aim? With what aim we are starting all these things? With what aim we are doing all these things? We have to find the Thevenin voltage and not on currents, right? Thevenin voltage and not on current. This is our Thevenin voltage 2V at the time T equals to capital T. This value we have to remember, which will be used in further calculation of Thevenin equivalent circuits. Okay. Yeah. Next. Let's continue like this now. Let's continue like this. Just observe what I am saying you. Switch was closed already. At time T equals to 0 plus, switch was already closed now. Right. And this is an open circuit. Open circuit. See, we have a current of I, voltage V, current I. Like that, we have a development already we discussed. That's why I'm not repeating. Already we discussed. And this is the time T equals to capital T. Time T equals to capital. Current is becoming 0 means what? Current is becoming 0 means magnetic energy is falling down to 0, na? Magnetic energy is falling down to 0. But you know, according to the basics of energy, energy neither created nor destroyed. It can be converted from one form to other form. So that the magnetic energy is going to be converted into electric energy. That is the other energy form available. Yeah, look here now. Look here. After reaching here, I2 value 0. So means current in the transmission line will become 0. Voltage will become double. Current is 0. Voltage will be double. Current is 0. Voltage will be double. How much is the time here after reaching to this point now? Back propagation we can, na? First propagation we have done. Now we are coming in the back propagation. How much time it will take for that propagation? Capital T only. Capital T only. Already we spent a time capital T. Now this capital T is added up, results into 2T time. Results into 2T time. And this is a point of x equals to 0. X equals 0. Let me write two propagations we have discussed. Propagation 1 and propagation 2. I'll write here only. Number 1. Propagation 1. This is from time T equals to 0 to capital T time. Time T equals to 0 to capital T time. We are not discussing about the open circuit voltage and the currents here. We are not discussing the open circuit voltage and the currents. We are discussing about only voltage and currents on the transmission line. Voltage and currents on line. Means we are going to write currents on the transmission line. On the transmission line, not in the open circuit. Don't ask me again in the doubt session. Yeah, please tell me. What are the voltage and currents on the line V comma I developing? V comma I developing. Okay. See, if you want, you look at the x also. This is from x equals to 0 to x equal to L. X equal to 0 to x equal to L. Second. From the time capital T to 2T. Capital T to 2T time. Yeah, check this. From the time capital T to 2T time. Capital T to 2T time. What's happening to voltage? Double. Current is falling down to 0. voltage is becoming double, current is falling down to 0. And what is the x location? X location, x equal to L to x equals 0, back propagation. X equal to L to x equal to 0, so called the back propagation. Back propagation. Yeah. Next, look back. All of you listen here. All of you listen. It's a propagation 2, na? Propagation 3 I am showing now. Look here kindly. Propagation 3. Propagation number 3. All of you, check what I am saying. And what's the voltage here at this place? At what time we are standing? 2t, na? Time 2t we are standing. Time 2t. What is the voltage here? V, right? Voltage is V. But what is the voltage on line you are saying? 2V. You are saying that voltage is 2V. We have a mismatch in the voltage. We have a source voltage V, line voltage 2V. There is a potential gap. Potential gap. Because of potential gap, what will happen? Because of the potential gap, what will happen? All of you, please tell me. Nobody is responding. Please tell me what will happen. Current starts flowing. Current starts flowing. From what point to what point? From 2V to V. 2V to V, current will start flowing. But our conventional direction of current is from source. Conventional direction of current is from source. So I can say negative current will be flowing in this direction. Negative current will be flowing in the direction. Or else you think in a general perspective, we have an inductor. One side we have V voltage, other side we have 2V voltage. Because of that voltage gap, current starts flowing in the inductor. Inductor is gaining the energy. Inductor is gaining the energy. On the behalf of that, this capacitor will be losing the energy. This capacitor will be losing the energy. Whenever it is losing the energy, at some point, this voltage will come V, na? At some point, this voltage will come V. At that point, you know, both sides voltages are equal. Both sides voltages are equal. Inductor energization stopped. Inductor energization will be stopped. Similarly, this side we have a voltage V, other side we have 2V. Because of the potential gap, this inductor starts carrying the current. Inductor starts carrying the current. Negative current it will start carrying, and this capacitor continuously losing the energy. So this voltage might become V. Like that you observe. At each and every point on the transmission line, we have a current of minus sign and we have a voltage of V. Comes back to this point. What's the time now? What's the time here? That will be 3t time. 3t time. From the time 2t to 3t. From the time 2t to 3t. Voltage, what will happen to voltage on the line? It will be modified to V. Voltage on the line will be modified to V. How is the current on the line? Modified to minus sign. Modified to minus sign. Clear? So I'll say here. So it's a third propagation from the time 2t to 3t. 2t to 3t. Means it is from the point x equals to 0 to x equal to L now. X equal to 0 to x equals to L. Voltage will be modified to V, current will be changed to minus. Current will be changed to minus I. Yeah. Please do it quickly. Fourth propagation, what will happen? Fourth propagation. Propagation number 4. Let's look here. It's also very simple one. The result of 3, na? So I'm modifying this number to 4. We are standing at which location? X equals 0 or X equals to L? Which location we are standing? X equal to 0 or X equals to L? At what time we are standing? At what time we are standing? 3t time. 3t time X equals to L. X equals to L. Okay, okay. What you have here? Open circuit. Open circuit means open circuit current will be 0. So current in the line must be falling down to 0 now because of the open circuit condition. Because of the open circuit condition, current in the transmission line must fall down to 0. See, current in the line is falling down to 0 means this energy will be released to the capacitor. This energy will be released to the capacitor. See, listen kindly. Earlier, in the first propagation, plus I current is getting discharged, right? Plus I current is getting discharged. Voltage is becoming double. Plus I current is getting discharged. Voltage is becoming double. Now, what current it is getting discharged? Minus I. Because of that minus I current discharge, this voltage will fall down to 0. Voltage will fall down to 0. All of you understood this? Right. Like that, minus I current is getting discharged means voltage will fall down to 0. Minus I current is getting discharged means voltage will fall down to 0. And what's the time now? That will be 4t time. 4t. So from the time 3t to 4t, voltage on the line will be 0. Current on the line also becomes 0. Okay. So I think all of you getting it. All of you getting this one? Yeah. So I'll show here. I will write here. This is from the time 3t to 4t time. Means I can say x equal to L to x equals to 0. X equal to L to x equals 0. Voltage is becoming 0. Current also becomes 0. Voltage and currents, both values will become 0. Voltage and currents, both values will become 0. And what will happen from this point? Please tell me. What will happen from this point onwards? Again, we have a voltage V, voltage start developing, current start developing on the transmission line. Means propagation 1 is going to be repeated. Propagation 1 will be repeated from the time t equals to 4t onwards. Okay? Yeah. So I'll write from the time t equals to 4t onwards, propagation 1 will be repeated. Propagation 1 will be repeated. Propagation 1 will be repeated. Yeah. So this is about the open circuit line wave propagation. So we have a break for 5 minutes. So after break, we start with the short circuit line wave propagation. 5 minutes break. So after break, we'll be starting with the short circuit line wave propagation. Yeah. So I have resumed the audio, video on screen. Resumed the audio, video on screen. So now I will be taking up with short circuit line propagation quickly. Short circuit line propagation. Next propagation we are calling short circuit line propagation analysis. Short circuit line propagation analysis. Yes. Let's have a look at this. Let's have a look at this one. So I'll be showing the same, what we call lossless line model. The lossless line model, LC elements. All inductors and capacitors are of equal in value. So, and at the end, like this, we can say. So this is a point x equals to 0, and this is a point x equals to L as it is. And I'll say that we have a voltage source here V. And the switch is going to be closed at time t equals to 0 plus. Yeah. So we have a short circuit at the receiving end side. We have a short circuit at the receiving end side. Short circuit at the receiving end side. And this is a junction J, so called the discontinuity point. And again, at time t equals 0 plus, when the switch was closed, a current of I, accordingly a voltage of V is getting developed along the line at all the places. Voltage V and the current I is going to be developed along all places. And after reaching to the junction, we have an incident voltage and current as V comma I. We have an incident voltage and current as V comma I. And we have refraction V2, I2, we are giving the names. Reflection, we are giving the names as V1, I1. And here ZL is equals to 0. Load impedance value was 0. And we have some characteristic impedance of the line like ZC non-zero number. ZL, ZC are becoming unequal. This ZL and ZC are becoming unequal. Because of that, we have some refracted quantities V2, I2, which will be definitely not equals to V comma I. That's why we are saying there will be some reflection as V1 comma I1. And this is happening at a time t equals to capital T. It's happening at a time t equals to capital T. Yeah. Next, let's continue. Let's continue like this. So if you want, I will write in the same way at time t equals to capital T, location x equals to L. Location is x equals to L. Incident voltage and currents. In bracket, you write that location also. Incident voltage and currents are V comma I. Incident voltage and currents are V comma I. Okay. What you have at the receiving end side? What you have at the receiving end side? ZL equals 0. We have ZL equals 0 means we have a short circuit. Huh? Short circuit means what generally in the short circuit? What generally in the short circuit? Voltage. Voltage. How much is that? 0. So as ZL equals to 0, the refracted voltage will be equals to 0. As ZL equals to 0, I can say that the refracted voltage will be equals to 0. Refracted voltage is 0. Okay, see, listen. After saying that refracted voltage equals 0, incident voltage is V, based on these two, we can find out the reflection voltage. What will happen to reflected quantity? Reflected voltage. So you call it as V1, which is nothing but refraction minus incident. Refraction minus incident. Refraction is 0, incident is V. So reflected voltage equals to minus V. Reflected voltage will come to be minus V. Minus V. Minus V. Okay, done. Next thing. Next thing. So again, in the same way of analysis, after a switch has been closed, V comma I gets propagated towards the end of the line. So after reaching to the junction, we are experiencing a short circuit. Voltage equals to 0 at the receiving end side. Then what should happen to voltage on the transmission line? What should happen to voltage on the transmission line? It should be again falling down to 0, right? Voltage on the transmission line should fall down to 0. But there exists some voltage because of the electric energy. So now, according to energy conservation, this electric energy must be discharged to inductor as inductor energy. So electric energy converted to magnetic energy, on the behalf of that, current flow in the transmission line gets increased. Current flow in the line gets increased. Okay, that point we have to write. Okay. So I'm writing here. Due to short circuit, V2 is equal to 0. V2 equals 0. So voltage on the transmission line, must be fall down to 0. Must be falling down to 0. That implies electric energy stored in the line. Electric energy stored in the line must be converted into magnetic energy. So this is that conversion, what it is taking place. Electric energy stored in the line must be converted into magnetic energy. So you can call here I square, which is nothing but C by L into V square. That implies I is equals to root of C by L into V. Root of C by L into V. So this is nothing but V by ZC. Small I is nothing but V by ZC. What do you mean by V by ZC? That will be capital I. That will be capital I. V by ZC is nothing but capital I. Then what is the resultant current on the transmission line? Already existing current is capital I, and the small I is added to that. Resultant current will become almost 2 times of capital. So the resultant current on transmission line, resultant current will be small I plus capital I. So it will be capital I plus capital I now. That will be 2I. That will be 2I. Okay. And can we call this as the refracted current now? This is nothing but refracted current. That is nothing but refracted current. Else you can call it as short circuit current at the time t equals to capital. That's nothing but short circuit current at the time t equals to capital. Or short circuit current at the time t equals to capital. Short circuit current at the time t equals to capital T. Here Yeah. So I think all of you understood this. This is that propagation 1, you can say. This is a propagation 1. Voltage V, current I, voltage V, current I. Let me write propagation 1 here. Similar way, what we have done earlier, I am writing. Right. So it's a propagation 1 from the time t equals to 0 to capital T. Voltage and currents on the line only, I'm writing. Voltage and currents on the line. It will be V comma I. Voltage and currents on the transmission line will be V comma I. V comma I. And that's from x equals to 0 to x equals to L. X equal to 0 to x equal to L. Okay? Yeah. Second propagation I'm saying. Second propagation. From the time t equals to capital T to 2t. Time 2t to, sorry, t to 2t. T to 2t time. Observe now. Observe now. Yeah. This is that first propagation model. Na? So let me copy the same. To show you the second propagation at least. Second propagation I'm going to show. Simple, very simple. And we are staying at x equals to L location at a time t equals to capital T, we said. The switch was closed long back at time t equals to 0. We are staying at a time t equals to capital T. Na? The switch was closed long back. And this voltage will be V. That voltage will be V, you know. Okay. Now, just look here, look here. V2 equals to 0. V2 equals 0. So, as we know, this current is becoming double. Voltage is becoming 0. Voltage is becoming 0. Current is becoming double. Voltage is 0. Current is becoming double. Like that, we are going to get the change. And what's the time after reaching to this point? Obviously 2t. Obviously 2t. So from the time capital T to 2t, from the time capital T to 2t, voltage is falling down to 0. Current is becoming double, 2i. Current is becoming 2i. So voltage is falling down to 0. Current is becoming 2i. And this is from x equal to L to x equals to 0. X equal to L to x equal to 0. Okay? X equal to L to x equals 0. Next, third one. From the time 2t to 3t. 2t time to 3t time. 2t to 3t. 2t to 3t. Means in this propagation, we can say in this propagation. Observe now. This voltage is V, but the line voltage is 0. Na? Source voltage is V, line voltage is 0. We have a potential gap now. Yeah, all of you please tell me now. All of you please tell me. Are you understanding this? Source voltage is V, but line voltage is 0. Line voltage is 0. We have a potential gap. Because of the potential gap, what will happen? This inductor is experiencing that potential gap. So inductor starts further energizing. Already 2i, okay, already 2i, but even more current will start flowing that because of the excessive potential gap. So this inductor current starts increasing continuously. On the behalf of that, this capacitor also gaining the energy because current is flowing in this direction. That excess current, what you say, that will be flowing in this direction. This capacitor also starts gaining the energy. So this voltage starts increasing. At some point, this voltage will be rising up to V. Current will become 3i. Voltage will be rising up to V. Current will become 3i. Again, we have a voltage V here, voltage 0. We have a potential gap between these two. Because of that, this inductor starts gaining the energy and this voltage will be modifying to capital V and current will become 3i. Like that, at all the places, current will become 3i and voltage will become V. And we reach it to this point, the time t equals to 3t. We reach it to the end, we can say that the time t equals to 3t. Time t equals to 3t. So from 2t to 3t, 2t to 3t, voltage will be remains at V, current will be 3i. Current will be 3i. Okay, so that's a third propagation. Voltage will be V, you can say, current will become, voltage will be V, current will become 3I. And this is a propagation starting from x equals to 0 to x equal to L. X equal to 0 to x equal to L. Next, fourth propagation you can say. Fourth propagation. And this will be starting from the time 3t to 4t. 3t to 4t time, you can say. Just check back. 3t to 4t time. 3t to 40. We have a short circuit. Because of the short circuit, this voltage will fall down to 0. That voltage will fall down to 0. Current will become 4I na, because of the energy exchange. Because of the energy exchange, current will become 4I. Like that. Voltage will fall down to 0. Current will become 4I. Voltage will fall down to 0. Current will become 4I. And we'll reach to the point x equals to 0. And this time you can say it is 40. The time you can say it is 40. So starting from the time 3t to 40, 3t to 40, voltage is falling down to 0, current is becoming 4I. Right. So voltage is falling down to 0, current will become 4I. 4I. Yeah. See, what will happen from 40 onwards? Tell me all of you. This is the time 40 and we have a voltage V here. Line voltage is 0, potential gap. Because of that, what will happen? Current starts creating and this current will become 5I. So 5I, voltage V, 5I, V, 5I. After reaching to the end, short circuit, voltage will fall down to 0. Current will become 6I, 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 6I like that. And again, voltage starts rising up. Current will become 7I. And then 8I, 9I. Like that you observe, current will continue to increase with respect to time. Okay. So you can say in this case, short circuit current continue to increase with respect to time. Short circuit current will continue to increase. Continue to increase with respect. Short circuit current continue to increase with respect to time. Yeah, we have done only 4 propagations. It will be continued. It will be continued further. We have stopped at only 4 propagations. That's it. Yeah, please wait. I will come back within 5 minutes and we will be discussing about conclusion about this open circuit and short circuit lines. And then we will see the Thevenin equivalent circuit also. So I have resumed the audio, video on screen. First of all, this is the doubt what the people might be having many times from the starting of this chapter. I think so. From the starting of this chapter, you have a doubt that why we are doing this transient analysis and what's the necessity of it. Why we are doing steady state analysis then? What is the necessity of doing the steady state analysis? To estimate the efficiency of line, voltage regulation, to know maximum power transfer capacity of the line, as well as to know ideal power transfer capacity, to know how we have to keep the loading on the transmission line, how much loading we can keep on the line. To know all these things, we have discussed the steady state analysis. What is the aim of transient analysis? Anybody? What is the aim of doing this transient analysis? Yeah. What is the aim of doing the transient analysis? Just to find out over voltage. Just to find out the over voltages, right? So how much maximum over voltage the system is going to experience, that we have to know, based on which we will be selecting the insulation level of the system. Following all of you? Yeah, you please tell me in the open circuit line case as well as short circuit line case, almost we have discussed 4 propagations now. What is the highest voltage? What is the highest voltage experienced by the transmission line? Experienced by the transmission line in any propagation. What is the highest voltage experienced by the transmission line in any propagation? That will be 2V. 2V is a voltage experienced. So I can say now maximum switching over voltage. It's a switching over voltage. We are doing switching transient study only. We are doing the switching transient study. Why? Why we are going to say this as switching transient study? Because we are keeping a switch here? No, because of the voltage source. Because of the existence of voltage source. Practically speaking, the source in the power system network will be a voltage source only. Voltage source. That's why we are going to call this as a switching transient study. When we will call it as lightning? Then we will call this study as lightning. If that voltage replaced with current. If that voltage replaced with current, moreover impulse current, then you can call it as lightning transient analysis. Okay, yeah. So let's continue. Maximum switching over voltage. Maximum switching over voltage experienced. OV I am saying, over voltage experienced. Maximum switching over voltage experienced. That will be 2V. That will be 2V. For what supply we are discussing this? DC. We are discussing this for the DC supply. If it is AC, what I should do? If it is AC, what I should do? I should take up this voltage as phase voltage or line to line. What voltage I should take? Is it phase or line to line? Insulation designed based on phase or line to line? Phase. We have to consider that as phase. Okay, phase. Is it RMS or peak? Is it RMS or peak? It should be peak value. So the highest, the maximum over voltage experienced by the transmission line will be 2 times of per phase peak voltage in case of AC operation. That's why we are not interested to do the AC transient analysis, because we are getting it now. We are getting that AC switching over voltage also by an extension of DC. So that you no need to do the AC transient analysis separately to know what is that over voltage and all in this basic analysis. Okay. So I can write maximum AC switching over voltage. AC switching over voltage experienced. That will be 2 times of per phase voltage peak. 2 times of the per phase voltage peak. Means you can write now 2 into root 2 per phase voltage RMS. 2 into root 2 per phase voltage RMS. So it is 2.828 P phase RMS. 2.828 P phase RMS. Else we can call sometimes this as 2.828 per unit. In per unit domain, if you want to call, you can write it as 2.828 per unit. We considered some worst conditions. One is lossless condition. Next one, open circuit. By using these worst conditions, you are getting this number. By considering remaining all worst conditions and all, opening, closing these and all, generally this switching over voltage for AC application, will lie in the range of 2.5 to 3.5 per unit. 2.5 to 3.5 per unit, right? So generally range of AC switching over voltage, will be 2.5 to 3.5 per unit. 2.5 to 3.5 per unit. That's the range. Why multiplying with 2? That's coming from previous discussion only, Pawan. Again, why you are asking same doubt? Maximum switching over voltage, I have written 2V. Where you got it? Open circuit line. I have not written anything direct here. All the things are coming in a sequence. That's it. Okay, let's continue with that starting point what we have discussed here. This is the thing what we said. Line terminate with a resistor, and we said we have to calculate the open circuit voltage and short circuit current. I think we are ready with these two numbers. Okay, with the help of this, we try to convert this what we call distributed model of analysis into lumped at the time t equals to capital T. Okay, so let me copy the same diagram, same heading also I can say. Lossless line terminated with a load resistor. Same thing I am copying. Same thing I am copying to this place. Yeah. Look here. At the time t equals to capital T. Okay, you draw this one quickly. And we'll write the open circuit voltage, short circuit current. By using that, we'll try to find out Thevenin impedance, and then we convert this network into Thevenin model. Same heading you take. No issue with that. The equations what we are discussing is important one. Reflected voltage, refracted voltage equation. 2 times the V phase peak. V phase peak you should take, not V phase RMS. Maximum overcurrent value, that depends upon the fault analysis. The discussed in fault analysis, that will give the maximum overcurrent. Not in this transient study. Yeah, so let's continue. So at the time t equals to capital T, if you write open circuit voltage, or you can say Thevenin voltage, VOC or VTH, any name you can use, that will be 2V. From open circuit line study, we have said that. Short circuit, or you can say not on current, IN, or you can say it is ISC. How much is that? 2I. That you are getting as 2I, just from the study of the short circuit line. Now, ratio between these two is a Thevenin impedance. With respect to x equals to L location. At the time capital T only. This is valid only for the time t equals to capital T. Thevenin impedance, ZTH. So which is V Thevenin by I naught on. So it will come to be 2V by 2I. So 2 will be cancelled out, and it will be simply voltage to current ratio. What is that voltage to current ratio? That is nothing but surge impedance of the line. ZTH, that is nothing but the surge impedance of the transmission line. Yes. Now, the Thevenin equivalent circuit, which is valid only at a time t equals to capital T, as well as at the point x equals to L, you can say. At the point x equal to L. Yeah. So just look at this one. V Thevenin I should keep first. V Thevenin should keep. This is V Thevenin, which is nothing but 2V. 2V. And we have to keep Z Thevenin now, which is ZC, of course, which is resistive in nature. We have mentioned. So this is the point of x equal to L now. That's the point of x equal to L. Point of x equal to. What we have to keep that point, keep at that point x equal to L, we have to keep that load resistance. ZL. We have to keep that load resistance ZL. And you know, this point voltage is V2 refracted and this current is I2 refracted. Voltage V2, current I2 at time t equals to capital T for x equals to L. Right? So this is our lumped model. Is our lumped model. Lumped model. Can you find out V2 from this one? Can you find out V2 just from voltage division? Na? Just from voltage division, V2 is equals to 2V into ZL by ZL plus ZC. I2 you can get 2V by ZL plus ZC. That's it. You can get V2 and I2 easily from this. V2 and I2 you are going to get easily. But after getting that V2, I2, refracted quantities, how to get reflection? How to get reflection? Reflected quantity will be equals to refraction minus incident. See, this circuit, whatever you constructed is used to find out only V2, I2. After getting V2, I2, we should get back to original one and we should say V1, I1 as refraction minus incident. Refraction minus incident. Okay? Yeah. So let's say, first I'll write this circuit is used to find only refracted quantities. Only refracted quantities. V2, I2. And you can say reflection will be equal to refraction minus incident. Refraction minus incident. What are the incident quantities here? Incident quantities will be as it is, V, I only. There is no change. There is no change in the incident quantities. Just you should remember that this is a circuit equivalent you constructed on the paper, but this is the original one on which we are doing the transient study. So incident will be V, I, still same. Notations, if you want to write V1, I1 here, and this is V2, I2. V1, I1, and then you can say it is V2, I2. Yeah, correct, Sadish. Next thing. So let's take up the calculations of refracted quantities quickly. First one, I am taking up refracted voltage. Refracted voltage. So I can say it is V2. The formula for that V2 is 2V into ZL by ZL plus ZC. 2V into ZL by ZL plus ZC. 2V into ZL by ZL plus ZC. Next, I am taking up one term here. Coefficient of voltage refraction. Coefficient of voltage refraction, which is V2 by V. V2 by V. Coefficient of voltage refraction. So it is a ratio between refracted voltage to incident voltage. Ratio between refracted voltage to incident voltage. Incident voltage. So I can say V suffix refraction. This is the notation I am using for it. Notation V suffix refraction. Refracted voltage by incident voltage means V2 by V will come like 2 times of ZL by ZL plus ZC. 2 times of ZL by ZL plus ZC. Okay. 2 times of ZL by ZL plus ZC. Yeah, next thing. Let's take reflected voltage. Let's complete voltage, then we will go for current. Reflected voltage is a next term we are naming. Reflected voltage V1, which is refracted voltage minus incident. Refracted voltage minus incident. What is refracted voltage? 2V into ZL by ZL plus ZC minus voltage. You take that voltage V common. By taking that common, you can get here ZL minus ZC by ZL plus ZC. Like this a term we are going to expect. ZL minus ZC by ZL plus ZC. Yeah. Next, let's take the coefficient of voltage refraction, which is the ratio between reflected voltage to incident voltage. Coefficient of voltage reflection. Voltage reflection. V suffix reflection is a term you can use here. V suffix reflection. So it's a reflected voltage to incident voltage. So it will come like ZL minus ZC by ZL plus ZC. ZL minus ZC by ZL plus ZC. Yeah. Next thing. Next, you go for currents. Refracted current you take. Refracted current I2. That is nothing but 2V by ZL plus ZC. Refracted current I2. Refracted current I2 will be like 2V by ZL plus ZC. 2V by ZL plus ZC. What is that voltage V? What is that voltage V we should say? That is nothing but I into ZC. That voltage V, incident voltage, is nothing but I into ZC. That I will use now. That I will use. So the current I2 will come to be 2Y into ZC by ZL plus ZC. ZC by ZL plus ZC. Now what is the coefficient of current refraction? Coefficient of current refraction. Simple thing. I refraction will be like 2 times of ZC by ZL plus ZC. 2 times of ZC by ZL plus ZC. That's the coefficient of current refraction. Current refraction. Take the current reflection. So you write reflected current I1, which is nothing but refraction minus incident. Refraction minus incident. So you can get here 2I into ZC by ZL plus ZC minus I. 2I into ZC by ZL plus ZC minus I, and you take the current common. So I can write here I1 is equals to, by taking that current common, you can get here ZC minus ZL by ZL plus ZC. ZC minus ZL by ZL plus ZC, like that. Just you simplify that expression, you will get it. Okay. This I will take minus common here, minus I will say. So it will be ZL minus ZC by ZL plus ZC. ZL minus ZC by, you can get here ZL plus ZC. This is I1. Now you can write coefficient of current reflection, which is I1 by I. Coefficient of current reflection, I1 by I. So it will be like negative of ZL minus ZC by ZL plus ZC. Negative of ZL minus ZC by ZL plus ZC. That's the coefficient of current reflection. Coefficient of current reflection. Okay. So these coefficients are very important for examination. Coefficients are very important for examination. Just listen to me once. Just listen to me once. I'll tell you the significance of these coefficients. Just look here. Just at some point, capital T. Talk about only voltage. Same thing can be taken up for the current also. Same thing you can extend for the current also. Just listen. At the time T equals to capital T, a voltage V was incident at this place. Voltage V was incident at this place. Okay, voltage V. After that voltage V was incident, what is the refracted voltage? What is it refracted voltage? That is nothing but 2V into ZL by ZL plus ZC. See, whatever the multiplication factor we have for that V, whatever the multiplication factor we have for this V, that I am taking up or taken out, that we are saying as coefficient. Means 2 ZL by ZL plus ZC we have said as coefficient. Means what I want to tell here is, after knowing the incident voltage, multiply the incident voltage with the refracted voltage coefficient, you get the voltage refraction value. Multiply the voltage reflection coefficient, you will get the reflected voltage value. I think all of you getting it. At some other time, we have different value of incident voltage, something like Vx. Some different value of incident voltage, we have something like Vx. After that, Vx was incident. What is the refraction? Vx into coefficient what we have calculated. Means Vx into 2 ZL by ZL plus ZC is a refracted value. What's the reflected voltage? Vx into ZL minus ZC by ZL plus ZC. Means my intention is to tell you, we have taken the heading as calculation at the time T equals to capital T and all. Calculation as time T equals to capital T and all. But after calculating these coefficients, whether these coefficients are valid to calculate the reflections and refractions at that particular location at any time. Please kindly tell me. Are you clear about it? Whether these coefficients will help you to find out the reflections and refractions at any time with respect to that location. Yes or no? Yes, simply at any time, whatever the incident we have, that you multiply with the coefficient, that will give you the respective reflection or the refracted quantity. Simple, very simple thing. Very simple. Okay. Fine. That's the aim of calculating these coefficients. And you have to remember these coefficients, right? Very simple. What is the voltage refraction coefficient? Voltage refraction coefficient is 2 ZL by ZL plus ZC. Voltage refraction coefficient 2 ZL by ZL plus ZC. What is the current refraction coefficient? Current refraction 2 ZC by ZL plus ZC. Current refraction is 2 ZC by ZL plus ZC. What is the voltage reflection? ZL minus ZC by ZL plus ZC. ZL minus ZC by ZL plus ZC. What's the current reflection? Negative of that. Means you have to understand that coefficient of current reflection is negative of coefficient of voltage reflection. Coefficient of current reflection is negative of the coefficient of voltage reflection. See, whatever the coefficient we calculated, that is independent on time, right? Refracted voltage, reflected voltage, currents and all depends upon the time. That's okay. But coefficient is independent on the time. That's why you can use that coefficient for the reflections and refractions calculations at any time, at that given location, at that x equal to L only, at that x equal to L only. Yeah. So let's take up a small table here. Coefficient, I will write here, coefficient. And I'll say for open circuit line, and then here it is for short circuit line. And last one I am saying it is flat line. Means I want to know what will be the coefficients for each and every category, each and every category. Four coefficients you have now. How will be that coefficient value for open circuit line, short circuit line, and then for the flat line? Yeah. First, coefficients I will write quickly. First, voltage refraction coefficient. Voltage refraction coefficient, how it is? Check. Voltage reflection coefficient, how it is? Current refraction coefficient, you write. Then you can say current reflection coefficient. Current refraction and then current reflection coefficient. Yeah. Just observe. First, open circuit line. Open circuit line means how much is the value of ZL? How much is the value of ZL for open circuit line? Infinite, you have to keep in all the four equations and you should fill this table. Short circuit line means ZL equals to 0, we should keep. Flat line means ZL equals to ZC, we should keep. Flat line means you should keep ZL equals to ZC. Yeah. Tell me first. For ZL equals to infinite, what is the V refraction? V refraction is 2 ZL by ZL plus ZC. So 2 into infinite by infinite plus ZC. It's coming like infinite by infinite. Infinite by infinite. Let's modify. 2 by 1 plus ZC by ZL we can write. Means numerator and denominator you divide with ZL. Numerator and denominator you divide with ZL. So you get 2 by 1 plus ZC by ZL. If ZL is infinite, ZC by infinite is 0. So 2 by 1 plus 0, number will be 2. So V refraction value is 2 for open circuit. V refraction value 2 for the open circuit line. Next, V reflection. V reflection. See this. ZL minus ZC by ZL plus ZC. Infinite by infinite. Infinite by infinite means you can get here 1 minus ZC by ZL by 1 plus ZC by ZL. And if you keep the ZL infinite, you get 1 minus ZC by infinite, 1 minus 0. 1 plus 0. So the value will be 1. V reflection value will be 1. V reflection value will be 1. Okay. I refraction for open circuit line. Just check back. I refraction 2 ZC by ZL plus ZC. ZL is infinite. 2 ZC by infinite. That will be 0. I refraction will be 0. I reflection, it is negative of the voltage reflection. Voltage reflection plus 1, current reflection will be minus 1. Okay. Yeah. Next, for short circuit line, if you see, short circuit line, ZL equals to 0. What is V refraction for ZL equals to 0? 2 into 0 by 0 plus ZC. 0 by ZC. 0. V refraction will be 0. V reflection. 0 minus ZC by 0 plus ZC minus ZC by ZC, it will be minus 1. Minus 1. I refraction. It will be 2 ZC by ZL plus ZC. If you keep ZL 0, so 2 ZC by ZC will be cancelled out and it will come to be 2. It will come to be 2. Okay. What is I reflection? Negative of V reflection, so it will be plus 1. Negative of V reflection, so it will be plus 1. If you take up for flat line, you may get this like 1 0 1 0 1 0 1 0. So I think all of you getting it. So in tomorrow class, we'll do some problems on these calculations of reflections and refractions, and then we'll move on to the voltage control. Voltage control. Okay. Yeah. So tomorrow the class will be starting from 6:30 a.m. 6:30 a.m. to 1:30 p.m. That's the schedule here tomorrow. 6:30 a.m. to 1:30 p.m. So at any cost, we should complete the voltage control by end of tomorrow. By tomorrow afternoon, we should finish the voltage control. Yeah, if anybody have doubts, you can ask me. Akshay.
Hello, sir. Am I audible?
Tell me, Akshay.
Yes, sir. My doubt is we found the maximum switching over voltage from the open circuit analysis, right?
Okay.
Then, like, what was the purpose of that short circuit analysis that we did? Short circuit line analysis.
Ultimate aim is to construct the Thevenin equivalent circuit to find out the reflections and refractions.
Okay. And like,
don't you need the short circuit current required, right?
Oh, yes, sir. Yes, sir. Got it. Got it. But like maximum over voltage, switching over voltage, we
that
can.
Is coming from only open circuit study.
Open
That's
circuit. Okay. Okay, sir. Got it. Got it. Thank you, sir.
Yeah. Vishnu.
Sir, my first doubt is in this starting itself only, sir. In this, you said that there's a constant, like previous class you mentioned, there's a transfer, energy transfer between the inductor and the capacitor. And from this capacitor, will go to the next inductor and so on and so forth. So my doubt is when this L and C are charging, wouldn't it work like an oscillator there?
No, see, continuously there is an exchange.
Even though it's a DC also, if you go with Laplace transform, L and C will form an LC circuit.
That's what I'm saying, Vishnu. There is a continuous exchange.
Oh,
so inductor is transferring its energy to capacitor does not mean that inductor energy is falling down to 0.
Okay, sir.
Inductor is gaining the energy from previous one, right?
Okay. All right. Okay, that's fine, sir. Because oscillator to work means entire energy of L must be transferred to D and then back to L.
It's not the thing, right?
That's okay, sir. And sir, when you explain this over voltage concept, that fourth case I couldn't get it, sir. How voltage becomes 0?
Which one? Short circuit or
open circuit?
So, initially, plus I current is getting discharged. You are saying voltage is double, right?
Yes, sir. That is
now
also
how much current is discharging?
Minus I, it seems.
Minus I.
Okay.
Current is flowing in the reverse direction, right? So capacitor is delivering current. That's the meaning there.
The capacitor is delivering current into the back.
Means it is losing its energy completely.
Okay, sir. Okay, that's fine. Sir, and last one is regarding this current, how it becomes 2I in the case of short line propagation, sir. Same
Again,
logic.
voltage
same
is
logic.
becoming zero means electric energy will be converted into magnetic energy.
Yes, sir. So the current will be flowing in opposition to that of the conventional direction of current.
No. You should think about that energy exchange in a proper way.
Oh, so this current, so
Not the last capacitor. You take the capacitor before to that.
Okay, so that will transfer this energy into the inductor that is in front of it.
Yes. Mhm.
Okay, sir. And so, okay, then by logic, then this capacitor must transfer this its electrical energy into that short circuit line. Sir.
Mhm. Yes.
So that's how we get to Y. And further, as time proceeds, it becomes 4I, 5I, 6I, 7I.
Like that, it's continuously increasing.
Sir, but then wouldn't it be a destructive process? Then as time goes to infinity, wouldn't it become infinite, or will it stop at some value? It should stop.
Practical line is what we call a lossy line, right?
So the resistor will
Practical
stop.
line, you have a resistor and it will settle down to some fixed number.
Okay, sir.
But it's a DC operation, lossless. In the short circuit condition, the current continue to increase. But in AC, it may not happen.
Due to the negative half.
In case of AC, because of negative half or because of the effect of the impedance, current will not increase continuously, right?
Yes, sir. Okay.
Yeah.
So that's it, sir.
That's it.
Okay. Thank you.
Ramakrishna.
Hello, good morning, sir.
Good morning, Ramakrishna. Tell me.
Sir, reflection is coming back, no, sir. You have taken as incident and incoming as both are same side.
Okay. Okay.
How I should be equal to I1 plus I2? No, you have taken I plus I1 equal to I2. You said it is added I1.
Okay, why can't it be?
Then the equations change.
What equations, Ramakrishna?
No, sir, nothing changed.
What I have written here, just to see once.
Yes, sir, okay. For understanding only it's
understanding.
Yes,
mathematically, I have written
yes,
here.
Sir. Yes, sir.
Yeah, that's addition. Addition is making up that resultant current. That's the meaning.
Yes, sir. Okay.
Haripriya.
Good morning, sir.
Good morning, Haripriya. Tell me.
Sir, in open circuit light propagation, once explain the direction of propagation, sir. From T.
Which direction of propagation you want?
From T is equals to T to 2T. Why it is coming back, sir?
Why it not coming back actually? Okay, you can understand in that way also. See, after reaching to the receiving end side, current will be zero.
Yes, sir.
So in the line also, current should become zero, na? So
Okay.
as the current is becoming zero, obviously voltage is also getting changed. So like that, at each and every point, current is changing, voltage is also changing.
Okay, sir.
That's the meaning of getting back towards x equals to 0.
Okay, sir. That's why actually I was getting confused from why it is getting back like that.
This is the direction.
Okay, sir.
Okay.
From 3T to 4T are the same, sir. Like
See,
that.
after reaching to this place, your line voltage is 2V, but your source voltage is V only. There is a potential gap. Because of the current will be created.
Okay, sir.
So that current will exist. Because of that current, again voltage will change, right, on the line.
Okay, sir.
Again, voltage and currents are changing on the line, starting from x equals 0 to x equals to L.
Okay, sir. Yes. Got it.
Okay. Yeah. So, any other doubts? Please raise your hands. Any other doubts? Please raise your hands. Navdeep. Navdeep.
Yes, sir.
Tell me, Navdeep.
Sir, my doubt is in its lossless line terminated with resistor load, sir. You said that at T is equal to capital T, VThevenin will be 2V, but it is V, sir.
Capital T is nothing but T plus only. Don't think about that.
Only
Capital
after
T,
T we have
capital
to.
T plus, both will be same.
Okay, sir. We have to not consider that it is only T. After that only we have to consider.
After that only. Just after T.
Okay.
Okay.
Hello, sir.
Tell me, Akshay.
Sir, one more doubt, sir. In like short circuit study, I just got this doubt. Like even though it's lossless, that the current keeps on increasing like to a very
because
high
DC
value.
operation, no.
Yes, sir. But
If it is AC operation, it will settle down to some value.
okay, but even then, like we feel that we are getting more energy, right, as time passes.
Okay, okay.
Like, should that happen in an ideal system? Like, even though there is no
What
loss,
happen
we are
in practical system, I am saying, right?
even in the ideal system, like there is no loss, so that the energy should remain the same, right? I feel that we are gaining more energy as time passes.
Who is supplying energy?
That I'm not sure, sir. But the current, like indefinitely, if it's rising, then it should mean that we are gaining some energy, right?
Yes, yes. Who is supplying that energy?
Not really sure. Source, I guess.
The source only is supplying energy. Who will supply energy other than source?
Okay, so source
Other than source, who will supply energy to you?
okay, so it
So
has
the
to
ideal source means
okay.
it's having a capability of supplying infinite amount of energy, right?
Oh, okay, yes, sir, yes, sir.
The source only supplying that energy.
Okay,
Yes.
okay. Got it, sir. Thank you, sir.
Manivannan.
Sir, the propagation which we did are actually for mathematical iterations to find the resultant transients, or every propagation there is actual value is in that manner, sir.
I didn't get you what you're asking. Please, can you repeat again?
Are we trying to find the final transient voltage and current?
After some time, it will reach to steady state. Sometime it might be reaching to steady state. That depends upon your circuit conditions.
Or it's just a mathematical iteration to find the real value after every correction, sir.
It's a mathematical thing which can be extended into a what we call continuous domain. We are doing this analysis in a discrete way. Step by step way, we are doing this one. But practical one is a continuous domain, na?
So exactly at the t equal to 2t, the current will be 2 times the ascending current. Like that, can I take?
Yes, you can take it.
Sir, in the final tabulation, you say the short circuit current is 2 into I. The coefficient is refraction.
Yes.
But we already in a propagation we went up to 2, 3, T3, 3I.
This is for only first time we have written. So only for first time, as well as at any time, if a particular current or voltage is attacked, you multiply with these coefficients, you will get the respective numbers.
Okay, for a first without any backflow.
Not only for the first. These are valid for any time.
So here the current at the open circuit, short circuit line is 2 times the sending in current only, right?
That incident is different, right? Okay. That respective incident you have to take. You should not take the starting incident only. Incident value will continuously change, na? Time to time now.
That's why I am asking, sir. At t equal to 4t, the current value is 4 times the current.
It won't come 4 times. It will be I only. That reflected current, how much you have? I, na? First capital I current was propagated. 2I is refracted. What's the reflection? I. That I will come back to the source location.
Okay.
That will experience a reflection. That reflection will come back to the load location. With that reflection, whatever you got, that will act as an incident, right?
Incident.
That incident will multiply with the coefficient to get the thing.
Okay. I
The
got
resultant value will be summation of all at one point.
So the initial incident should not be taken in that I. Okay.
No.
But before that, okay. Thank you, sir.
Yeah. Shraddha.
Hello, sir.
Tell me, Shraddha.
Sir, 3F slide.
Okay.
Sir, as initial condition, we have considered inductor acts as open circuit and capacitor acts as short circuit. But here in this diagram, inductor is acting as short circuit.
Why?
Here, according to this diagram.
Why?
That's what, sir, I'm not understanding.
Where I have written short circuit for inductor? Have I written anywhere?
No, sir, but according to this diagram, this line, lossless line, we have taken.
Which diagram? First diagram or second diagram?
Second.
You show me L and C in this way.
But sir, series
You
inductance.
show me inductor and capacitor in this way. Yeah.
Sir, I didn't understand.
This is a practical line.
Okay.
This is a converted model.
Okay.
In converted model, you have drawn it on the paper.
Okay. So is
Showing
it just
property of line as L and C.
Okay, sir.
But practical line, I can't see L and C, right?
Yes, sir.
Hmm.
Okay, sir. And also the Thevenin equivalent circuit, how is it applicable for all the cases?
All the cases means?
Like for a T, 3T, for you said no, for all the cases for
The
T.
Thevenin equivalent circuit is valid only for the time t equals to capital T.
Okay.
The coefficients what you calculate, which are independent on time, na?
Yes, sir. Yes.
That those coefficients are valid at any time with respect to that place.
Okay.
For example, you have refracted voltage 2V into ZL by ZL plus ZC, na?
Right.
Incident voltage may change with respect to time.
Yes, sir.
So that the refracted voltage may change with respect to time.
Yes.
But whatever the coefficient we have there, 2ZL by ZL plus ZC, that will be remains constant with respect to time, right?
Yes, sir.
That's the thing I am saying. This one.
Okay. Sir. Yeah. Thank you, sir.
Okay. Swain.
Yes, sir. Good morning, sir.
Good morning. Tell me, Swain.
Sir, here you mentioned a point that energy can neither be created nor be destroyed.
Yes.
Okay. In that transmission line, we are not connecting any type of load.
Okay.
And then we can say that the voltage source will be not going to give any type of
Net
power.
energy output by the voltage source is 0.
Okay, 0. Then that can we say that inductor and capacitor are only due to the excitation only, means energy is not storing, only inductor and capacitor exchanging energy.
Yes.
Means here also it is valid that energy neither be created nor be destroyed.
Yes, correct only.
Okay. Then sir, another point is the magnetic energy stored in the line must be converted to the electrical energy.
Yeah.
Here, half CB, that voltage is stored in the transmission line will be valid for all the time. Means this will be for fast calculation. You have calculated V is equals to I into ZC for starting. How your process will be started. Then after that, that same process is means we are calculating on by seeing the transmission line conditions. We are calculating not by energy. If you go for calculating by energy, it is also valid.
It will be valid, but it's a discrete analysis, Swain. We are doing this as a discrete analysis. You go with a continuous domain, there will be a change. Okay. Ultimate final number will come as 2V or 2I, final number.
Okay. Okay. Means after just seeing it, we can calculate it. Means
yes.
like we done it. Okay. Thank you.
Anybody having doubts? Please raise your hands. Yeah, so I think nobody's having a doubt. Thank you.